students, welcome to this 9th lecture of the course Electrical Distribution System Analysis, and the title of today's lecture is Lumping Loads in a Geometric Configuration, and we are going to see triangular configuration today. In the last class, we have seen the rectangular configurations where we have tried to derive the voltage drop and power loss equation for rectangular configurations, and we have seen that for voltage drop calculation we can lump the load at the middle, and for power loss calculation we can lump the load at 1/3 of your length of your feeder. We have also seen the application of it where we have found out suitable voltage level for feeder so that drop will be within the limit of plus minus 3%. In today's lecture, we will see triangular configuration. As we have seen in the last lecture, various geometrical configurations can be used for getting approximate value of voltage drop and power loss. In this case, consider this a triangular area here. We can assume that substation is somewhere here, and then there are actually primary feeder which is going in this area, and then there will be laterals which are connected to the primary feeder, and these laterals are supplying power to the various consumers which are inside this particular area. To do the approximate analysis, as I explained in the last class, we are assuming load density over this triangular configuration is constant. So, this constant load density, as I explained in last class, we can say it is kVA per kilometer square area, and impedance of this feeder is in ohms per kilometer, which I am representing by small z. And as I explained in last class, that is capital Z I am using for total impedance of the feeder. So, small z is for impedance per kilometer and capital Z is for total impedance of the feeder. So, in triangular configuration also I am considering the length of the feeder is L here, and the width at the end of this triangle is W, and the total current which is going inside this triangular area is IT, and as I told you, we are interested in calculating voltage drop from this point N to M as well as power loss from this point N to M. And as we have seen in the last class for rectangular area, here also we will try to find out dV, which is voltage drop which is happening in small strip of length dx at a distance x from the source end, and then after integrating this dV for the length L, we can get total voltage drop. Similarly, we will calculate power loss dP which is happening in this small strip, and after integrating it from 0 to L, we will get total power loss. So, let us see the voltage drop first. So, if you know the total kVA, we can easily get the current which is entering to this particular feeder, which is given by this equation here, which is just your kVA divided by √3 times your line to line voltage. And then there is cos inverse of power factor, where this power factor is average value of power factor over your distribution area. In this case, this total kVA supplied will be nothing but load density, which is kVA per kilometer square into area, will give me total kVA which is supplied in this particular area. So, we can get total current which is entering to this area by knowing the load density. Once I get that, I can get the current density, which is nothing but total current divided by area. So, in case of triangular configuration, your area will be 1/2 L multiplied by W. where L is length and W is actually width at the end. So, it will become twice of IT divided by L multiplied by W, and since it is current density, it will be in ampere per kilometer square. As I told you in last class, we are interested in calculating your dV, and to calculate dV we want to calculate current, and then we want to calculate impedance, which is Z multiplied by dx, and real part of I multiplied by Z dx will give me voltage drop in that small strip, which is dV. So, to calculate that we first need to calculate current which is entering to this small strip, and then till this point or till this strip dx here, some current will get supplied in this area, means current will go on decreasing. So, if you calculate that current I here, so total current minus current which is supplied in this triangular area just before your strip is A1 multiplied by your current density. Area multiplied by current density will give me current which is supplied in that particular area, which is just before your strip. Let us see how to get this A1 here. To get A1 we need to know x and we need to know w. So, it will be just 1/2 x into w1, and this w1 we can write in terms of w. For that we can just consider this here. So, x by L, they will be equal to w1 by w because they will be proportional. So, proportionality of x and L will also remain in w1 and w. So, from this I can just write w1 will be equal to x divided by x multiplied by w divided by your L here. So, I can get w1 in terms of w. So, from this I can write equation for area. So, area will be 1/2 w1 into x, and w1 we have written in terms of x and w, which is right it here, and then this will be nothing but your area. This will be nothing but your area of triangle, just triangular area just before your strip. From that we can actually put this A1 into these equations, so that I can get the equation of current. So, as I told you, this A1 triangular area I am putting into this equation here. So, finally, it will be current equation will be IT minus this is nothing but your A1 and this is nothing but your DI, which are written here. So, this is your DI and this is your A1, and if you simplify it, this will become L square here, and this A square will remain here, WW will get cancelled out, and if you take IT out, these two also will get cancelled out. If you take IT out, I will get equation for current, which is this one, and then I can easily write the equation for dV, which is voltage drop which is happening in this small strip, which is real part of impedance Z dx multiplied by your current, and current equation which you have got it here I can just put here. So, it will be Z dx multiplied by your current which is entering into this strip. So, to get total voltage drop across the feeder or till the end of the feeder, we need to integrate this dV from 0 to L. So, total voltage drop across the feeder will be integration of this dV from 0 to L. Equation of dV we obtained it here, I can put into this expression, I will get this equation here, and in this case also your Z and IT they are constant, I can take it out, the remaining term they will be getting integrated. So, they will be under integration, and if you calculate the integration of this will one will be x, and integration of x square by L square will be x cube by 3 L square, and the limits of integrations from 0 to L, when you are putting it 0 it will be 0 only, and then when you are putting L it will be L minus L cube by L square. So, basically it will be nothing but L minus L by 3. So, it will become 2 by 3, and this there will be one L here which is multiplied by your Z will give me total impedance. So, finally, your this will be nothing but your total impedance, and the total voltage drop which is happening will be 2/3 Z multiplied by your IT. So, from this equation we can easily find out the lumped load model of triangular configuration. So, this is your voltage drop equation, and I can see that this 2 pi 3 into Z total Z multiplied by your IT. So, at this tells me at 2/3 distance I need to lump total current. So, that is why at the 2/3 distance I lumped total current, and this will give me correct voltage drop. And as we have seen, this different load currents can be lumped at different locations like earlier cases. Now, let us see the power loss equation. So, current equation which you have derived, which is entering into the strip, which is given by this equation, we already seen it. Then power loss which is happening in the small strip will be nothing but 3 into resistance of the strip which is RDX, and current entering into the strip which is I square, and we already got the current, we can put into this equation which will give me dP which will be equal to this is nothing but your radius resistance RDX and current square. So, current square means it will be IT square multiplied by this bracket square here. So, when you are taking square it will be whole square. So, it will be IT square and this bracket square here. So, if you square this bracket here I will get this term here. So, this is nothing but your power loss which is happening in this small strip area. And as I told you, to get the total power loss you need to integrate this dP from 0 to L. So, in this case we need to integrate this dP here. So, I can put this equation of dP into this expression, I can get this expression here, and in this case also your R and IT they are constant, I can take it out of integration. So, what will happen is we need to integrate this term here from 0 to L, and if you take the integration of these terms, integration of one will be x, integration of 2 x square by L square will be 2 x cube by 3 L square here, and integration of x 4 by L 4 will be x raised to 5 divided by 5 L raised to 4. And in this case the integration of limit is from 0 to L, and if you put these limits into this expression I will get this simplified term here, and this term is nothing but your 8 by 15 into L, and this total term will be 8 by 15 into L, and this L into this resistance will become your total resistance of the feeder which is nothing but your R here, and IT square will remain as it is. So, overall power loss which is happening in triangular configuration is given by this particular expression, and from this expression you can easily find out the location of your lumped load. So, from this we can see that at 8 by 15th distance or resistance value of 8 by 15 I can lump total current. So, total current will be lumped at 8 by 15th distance. So, we have got actually we have got the voltage drop equation, we have got power loss equation. Let us see this example here. In this triangular area I have considered length of the feeder which is 4.5 kilometer. So, this is 4.5 kilometer, this is width is 1.8 kilometer. Therefore, area of the triangle will be 1/2 length into width of the triangle, which will be equal to 4 by 4.14 kilometer square, which is area of the triangle. Then let us assume the load density into this triangular area is 1351.8 kVA per kilometer square with 0.9 power factor lagging. Again, this is average power factor over this area. Then total kVA will be load density multiplied by area. So, we have got area here, we have got this density here. So, density multiplied by area will be nothing but total kVA which are served into this particular triangular configuration. So, if you calculate that, it comes around 56.45 kVA. Let us say K drop factor of this feeder is 0.002191% drop per kVA per kilometer, and K rise factor is 0.000250% rise per kVAR per kilometer. So, K drop factors and K rise factors are given here. Let us say nominal voltage of this feeder is 11 kV, and in this particular example we are interested in finding the location of capacitor bank. So, suppose I have capacitor bank of 1800 kVAR and I want to put this capacitor bank somewhere in this feeder such that voltage at this end will be within the limit for given kVA. Means to supply this kVA there will be voltage drop from one end to another end across this feeder, and I want to put this capacitor bank somewhere along the feeder, and the capacitor bank which I am having is 1800 kVAR. Let us see how we can find out this location here. So, total load of triangular area which we have calculated on the last slide is given here. Now, using K drop factor we can calculate actual drop without capacitor. So, actual drop, so K drop factor we know that kVA percentage drop per kVA per kilometer. So, if you can multiply this K drop factor by kVA and kilometer, we can get voltage drop. In this case, since I am using lumped model, we see that we need to take, since the total load is lumped at 2/3 distance, we need to take distance to be 2/3 here. So, 2/3 of total distance is taken here. So, K drop factor is 0.000291 which is given, kVA served in this area which is also given, and then distance is, we have seen it is 4.6 kilometer, and we have to take 2/3 of that distance, and if you can calculate it comes around 3.76%, and we can see that we want this within the limit of plus minus 3%, and here the limit of plus minus 3% is getting violated. Now, to avoid that we need to raise the voltages over the feeder, and those voltages can be raised by putting the capacitor along the feeder, and we would like to calculate the location of that particular capacitor. Voltage drop due to the load is 3.76 which you have got on the last slide. However, it is violating that limit. We want to keep this within the 3% limit. So, 3.76 minus 3. So, we want raise of 0.76% which is getting violated. So, for raising this voltage by 0.76% at the end, we need to put this capacitor, and to put this capacitor we can see we can use your K rise factor, which is given here, which is 0.0002504% rise per kVr per kilometer, and by definition your K rise factor is V rise in percentage divided by your distance multiplied by kVr. So, we can see that I can easily write distance will be equal to V rise divided by your K rise multiplied by kVr. So, by using this equation here, distance can be easily calculated. So, the raise which we want by this capacitor is 0.76%, K rise factor is given, and the capacitor which I am having is 1800 kVr. So, if you calculate that, it gives me the distance is 1.69 kilometer, means we need to put the capacitor at a distance 1.69. So, let us say this is 1.69 kilometer, and I need to put this 1800 kVr capacitor at this location, and because of presence of this capacitor at this place, voltage at the end here will get raised by 0.76%, so that it will be within the limit of plus minus 3%. So, it will get raised by this value, and we will get actually required voltage limits without violation. So, in this particular chapter we have seen the geometrical configuration, which is triangular. So, if your area is having triangular kind of configuration, which I have shown on the right hand side figure, many times this kind of triangular configuration exists in your distribution system. So, in that case we have seen that we can lump these load at one location. So, in case of triangular configuration, we need to lump total current at 2/3 length for voltage drop calculation, and for calculation of power loss we need to lump this load at 8/15th distance, and the lump load will be actually total load. So, from seeing this equation we can easily find out these lumped models for triangular configurations. We also seen the applications of these equations which are derived, so that we can find out the correct location of the capacitor. If I am having some capacitor with me, I can find the correct location of that capacitor. It can be also used to find out the size of the capacitor if you know the location. Suppose at the end I want to put some capacitor which will raise the voltage to the required value, then size of the capacitor also can be calculated, because in that case distance will be known, that is that up to the end of the feeder. Okay, so, many ways we can use this equation to find out the capacitor sizes as well as capacitor placements. Thank you.